Boys hide behind their laughter like they don't care what girls think. We'll never.
Hi, everyone. Welcome to SF Big Analytics. My name's TJ. I'm one of the organizers. So today we have two pretty interesting speakers. But before we get to that, I'd like to thank our hosts, Yelp. We've done quite a few meetups here, and they always treat us really well, including recording the show, doing all the setup, and all those things that goes along with the meetup. So I'd like to thank them. And of course, they're hiring. So if anyone is interested in engineering jobs at Yelp, then Rebecca, all the way in the back, she's waving. So please speak to her after the meetup if you're interested in working at Yelp. My company also is hiring, Alpine Data. So if you're looking for jobs, talk to me. So we have a pretty interesting topic today, I think. So it's Apache Flink. And we have two speakers from Data Artisans. So first of all, we have Kostas Zumas, the CEO, who is going to give us a sort of overview and introduction. And then he's going to hand off to Jamie Grier, who is the Director of Application Engineering. And he's going to give a full demo. So please help me thank the speakers. Welcome the speakers.
All right. Can you guys hear me? Cool. All right, so hey, thanks for coming. My name is Kostas Zumas. I started Data Artisans 2 years ago. Started working on Flink about 6 years ago. I started working on database systems about 10 years ago. Today, I just want to give a very brief sort of teaser of what has been going on in the Flink community over the last couple of months. It's a lot. And then I'm just going to hand off to Jamie, who's going to go into a lot more detail and deep dive. So who are we? We're Data Artisans. We are basically the original creators of the Apache Flink framework. This is a company that was essentially born out of the Apache Flink community. Most of the Flink committers are Data Artisans. And we are also providing the DA platform, which is a commercially supported by us distribution of Apache Flink. So I'm not sure if you have been following Flink. If you have, you might have seen Flink Forward 2016. Flink Forward is the annual Flink conference. This was the second time we had this conference in Berlin. This time it was sunny and just and hot, yeah. So just a few, snippets of what happened there. So a bunch of big organizations sponsored the conference. We had a very interesting lineup, about 45 speakers from all over the place, large-scale Flink users, contributors, committers to Flink from several tech companies that are contributing. So from several companies, speakers from the likes of Uber, Netflix, King, New Relic, of course, Data Artisans, et cetera, et cetera. And really, if I look back sort of a year ago to the first conference and I compare it to this conference, the main takeaway for me was a maturation, both of the technology, so both of Flink, but also the applications that people are building with Flink. So we saw, use cases from the retail space, folks trying and successfully building better product recommendation systems. Folks from the finance space that are building sort of real-time products for banks or fraud detection systems. Folks from the general infrastructure, telco and IoT space, monitoring infrastructure, issuing alerts when something goes wrong. And of course, internet and mobile companies, click streams, user logs, getting all this data, doing analytics on this data, having the real-time user activity sort of at your fingertips. And another thing that we saw was a much larger scale of Flink deployments in several dimensions. And these are just 3 examples. So Alibaba has been using for a while a system based on Flink that is actually live, powering their product recommendations, and they have been and they're running this on they're running streaming jobs there on a 1,000-node cluster, processing millions of events per second. So, like obviously, one aspect of scale, one dimension of scale is how big of a cluster, how many resources are you using for that, and that was actually quite impressive. Another very interesting dimension of scale is how much state do you keep in the streaming computation. And there, I'm not sure if you have heard of King. King is a company that develops mobile games. They make Candy Crush, among others. So they have been running Flink jobs. They have built a system that is based on Flink, where they give access to real-time data to their data scientists. And they are actually maintaining hundreds of gigabytes of state 24/7 with exactly 1 guarantees, which is also quite impressive in that dimension. And this third company, they are the third largest telco carrier in France. They have actually been running Flink applications. They have 30 Flink applications in production for more than a year, and they're processing 2 terabytes per day. And one of their applications of the telco carrier is actually this one. So this is an actual room in their headquarters in Paris, where there are people actually sitting there, and they are monitoring how is the mobile signal, what is the health of the mobile signal in France, and what is the health of the landline signal in France. So they have sort of these indicators here, how this is evolving, and they have a map of France where if there's an outage or if there's something wrong, things are popping up. And this is actually powered by Flink in the backend, so I thought it was pretty cool. Next is, so if we sort of take a look back, right, and the whole stream processing space is by now quite confusing. So there are a million projects out there. There's a new thing coming up every day. So what is really needed, and what is Flink's role in this broader ecosystem? So if I would try to describe it in one slide, I think the contribution that Flink sort of brought to this industry was that before Flink, users of stream processing frameworks had to make hard choices, and they had to navigate trade-offs between a bunch of things, including what is the volume of the streams that I can process, what is the latency that I can achieve, and what is the accuracy that I can achieve. Yeah. So several times you could get sort of 2 out of 3 or 1 out of 3, but never all of these 3 together. And what Flink really brought to the table was that you no longer have these trade-offs. Yeah? So Flink has been demonstrated to process efficiently tens of millions of events per second. That was actually in a small cluster of 10 nodes. And at the same time, the framework can scale to thousands of nodes. So you can get very, very large volume. You can get your latency down to single-digit milliseconds. And you can get accurate computation results. And here by accurate, I mean both accurate in terms of failures. So if something fails, then your results should be as if nothing failed. Accurate in terms of downtime, and also accurate when your input stream is out of order. So when your data does not arrive in a very well behaved order. And Jamie will actually show you that in action in the demo. So really, in the end, what this means is that if you have a stream processing framework that you can depend upon, people end up building or moving more applications to stream processing. So applications that before were built using, repeated Hadoop jobs that are running every hour, or sort of standalone Java applications that are not fault tolerant, or any kind of other technology or mix of technologies. When you have a framework that guarantees all of this, you can actually feel much safer, moving your live applications to streaming. So the next question is, are we done, right? No, not yet. So there's a lot more to do, and the Flink community is busy working on several things. Again, if I had to sort of abstract it away from 10,000 feet, I would say that there are 4 major things that are happening. The first step for Flink, and that has been largely done with the 1.0 and 1.1 release, is provide state-of-the-art stream processing capabilities, things like event time, checkpoints, save points, etc. The next thing that is happening right now in the Flink community is make Flink operational and running in production in some of the world's largest streaming infrastructures. So some of the world's largest users of stream processing are now deploying Flink. They are working together very, very closely with the community and pushing the whole sort of operations part of the framework forward. The next thing that is very interesting is actually opening up stream processing, Flink and stream processing in general, to a wider set of users that are not necessarily Java developers or Scala developers. And one thing that is happening there is the addition of Stream SQL. So the last release of Flink, Flink 1.1, had the first version of Stream SQL. But what is happening now is that we're working very closely together with the Apache Calcite community, which is sort of the query parser and optimizer that's used by Hive and other projects, to bring into SQL the concepts of windows, the concepts of time, and all of the concepts that are needed for stream processing. And finally, the final thing is broadening the scope of stream processing beyond what now is considered mainstream. So right now, if you ask most folks, what is stream processing good for? The typical answer is real-time applications or near real-time applications where I need low latency. But that's not necessarily the case. Actually, stream processing is a great technology to create high latency applications that don't need necessarily low latency, but are running continuously and you depend on them. And this is just one example. If you take a look at the last release of Flink, Flink 1.1, these were the major features that were introduced by that release. So a bunch of new connectors, in particular Kinesis and Cassandra, not a metric system, a metrics system, so a system to expose metrics to monitor Flink. The first version of Stream SQL, session windows, and enhancements to the libraries, especially to the CEP library. Now, if you take that and add what the community is right now working on, you sort of get this. So it's kind of a lot. And to navigate all of this development, we can actually split it up in a few categories. So there's a bunch of work going on, and this will always be going on, integrating Flink with the wider ecosystem. So major threads there is integration with Apache Mesos, which should come in the next release, and a lot more connectors to get data into the system and out of the system. Another, let's say, category is opening up Flink to a wider set of users, so making things simpler. Yeah, so you can do the same things, but you can do them much, much more simply. So one thing here is the whole Stream SQL work, and the other is a DSL for defining windows. There are several application features that are coming in, things like queryable state, side inputs and outputs, etc. But what we can see is that the bulk of the work is actually about operations and making Flink operate in production at very large scale. So things there are things like security, fine-grained recovery, compatibility of checkpoints with save points, maintaining very large state that actually goes beyond hundreds of gigabytes, making resource management dynamic, and scaling programs dynamically while they're running. So there's a lot of exciting work going on. I don't want to take too much of your time, but if I had to summarize, right? So what is happening right now is that we're seeing the adoption of Flink accelerating, and especially in very large organizations that are very heavy-duty users of stream processing. The community the work that is happening in the community, if you look at it, is very, very much focused on operations and operational features. Also, adding Stream SQL to make stream processing more accessible to everyone. And something I did not go into detail was really this thing about broadening the scope of stream processing, which is actually enabling stream processing to be mature enough to take applications that are currently written using batch processing tools, using database systems, etc. If you want to learn more about Flink, I wrote together with Ellen Friedman a very short book, so it's about 70 pages. It's a light read. It's intended both for technical and non-technical folks. This was sponsored by MapR, and you can download it for free from the MapR website. So you can just Google MapR Introduction to Apache Flink, and you will find it. And then we're hiring as well, obviously. Also in San Francisco.
Thanks.
Okay, you guys hear me all right? All right, thanks for coming out tonight. It's a nice turnout. It's really good to see. Thanks to Yelp for hosting us here. It's a very nice space. The topic tonight is robust stream processing with Apache Flink. So I'm going to focus on the things that are important if you're doing stateful computation over streams and also trying to do this stuff correctly in production, and how do you actually manage this stuff, and how what stateful stream processing is all about, and sort of what kind of features you need to have in a stream processor to do this stuff correctly. Quick background about me. I am currently at Data Artisans. I'm the Director of Applications Engineering. I have been a coder my whole life, and at Data Artisans I've taken a little bit higher level role in the company. Basically, my job is to work with everyone in the community. I make myself as available as possible to help people that want to build stuff and get it into production on Flink. I try to just make myself available to help, which is a pretty great job to have, obviously. There's a lot of freedom there, and it's actually been great. My background is working on streaming computation. At a couple of different companies. Most recently, before Data Artisans, I was at Twitter, working on the streaming compute team there. Prior to that, I worked at a company called GNIP, which was later acquired by Twitter. Also a stream processing company at its core. We built something there sort of similar to Samza before any of this stuff really existed and stream processing was a thing. And like high-speed video stream processing before that. So kind of been my career. Is this thing working okay? Yeah? Okay, so the overview. So what we're going to talk about tonight. First of all, what is Apache Flink? How many people know anything about Flink to begin with? There's a few people, yeah. I'll give kind of a quick overview of what it is and where it came from. Just add a little bit to what Kostas talked about. And then I'm going to give what I call the world's quickest introduction to stream processing, and then specifically stateful stream processing. And then for the rest of the talk, we're pretty much going to write some code, and I'm going to demonstrate various things to I think it's just easier to get the concepts if we can just show how it works. So that's going to be the majority of the talk, is actually live coding and demo and stuff. So it's kind of fun. We are going to talk about windowed computation over streams. The reason this is important in stream processing is because you have unbounded data sets, right? So if you want to do something as simple as just consume a data set, group by key, and sum or something like that, you have to define a window simply because you can't wait for all of the data because there is no end to the data. So you define windows over streams and then compute on those windows. So if you're doing analytics, it's you sort of have to. I mean, you can do running sums and things like that, but typically you're dealing with various kinds of windowing. So we'll demonstrate some of that stuff. Then we're going to talk about these how Flink handles things in a more robust fashion than maybe we're used to in stream processing. So first thing we're going to talk about is time. How do you robustly handle time in stream processing? How do you robustly window over data that comes completely out of order with respect to time, but still do accurate analytics? So that's going to get us into this topic of event time versus processing time. And I'm going to demonstrate some things to make the difference obvious. And then We're going to talk about robust failure handling. So we're just going to actually show how Flink handles failures and manages state in the case of failures. Talk about how you do things like planned downtime. The one thing that's tricky about stateful applications is, there is no sort of time when you can just like shut down the system and like bring it up fresh and like go to some zero state. That's not how stream processing works. These are 24/7 applications that are constantly creating and computing and managing states. So you can't just like shut it off and like come up in the zero state and expect to like kind of be able to do the analytics you've been trying to do. I can demonstrate it, it'll make a little bit more sense, but the point is like if you have to shut things down, how do you like save all the state of the system and bring it up in a consistent state? Because if you're doing something like calculating hourly or daily aggregates, you got all this state, all these windows, and all this stuff in flight. You can't just shut it down without like somehow managing all that state and come back up. So not if we're trying to do robust analytics, right? So we're going to talk about that, and then we're going to talk about how to reprocess data. So reprocessing data is just a real-world thing where you've been running this streaming job for the last 6 months, the last year, and you find that there's some new aspect of the data you're interested in, or you find a bug in your code. So maybe it's not you're going to process all the data, but like a week ago you introduced some bug. You actually just, in the real world, this happens all the time, you just want to like go back and reprocess the last week's worth of data. And people are always building like these sort of ad hoc solutions to this problem, and maybe they use a batch processor to like do some stuff, and it's got similar code, and it's quite complicated. So we're going to talk about how to do that easily and correctly also. So we're going to try to get through all of that in the next 45, 50 minutes. Okay, so what is Apache Flink? Apache Flink is an open source platform for distributed stream and batch data processing. I want to emphasize here, and then we're not going to talk about it for the rest of the time, that Flink is actually a really fantastic batch processor. Its genesis was actually applying like a streaming data flow engine to the batch processing world, because it's actually a really good way to do things. Just as an example, like if you pipeline shuffles, you can end up doing things much more efficiently. So the original project was how to apply a real streaming engine to batch workflows. However, stream processing in the last years has become really very, very popular, and people, when you have a streaming data flow engine to begin with, it turns out it's a super good stream processor, as you'd imagine. So that's been the focus for Flink for quite a while. But there's a lot of people actually doing batch processing on production now, at a fairly large scale, actually. But we're going to talk about the stream processing side. This is kind of a quick picture that probably needs to be updated a fair amount, but basically the point is Flink is deployed a few different ways. If you're a Yarn user, you can deploy it on Yarn. You can actually deploy it on Mesos now, but there's more there's more native support for Mesos coming in the next. It's actually in master now, but in 2 months it should be released. So if you want to deploy on Mesos, Kubernetes, Docker, et cetera, you'll be able to do all those things. This is the runtime. So there's just one runtime. It's this distributed streaming data flow engine. And then there are a couple of different APIs. There's the dataset API, which is sort of like the batch processing world. Another way to think about this is you have a bounded dataset. So that's the dataset API. You have an unbounded dataset. That's the data stream API. So we're going to talk about this tonight. And then on top of these things, there's some higher level libraries as well. Complex event processing, the table and relational, and I should add SQL API here. There's a machine learning library, a graph processing library, and same thing. There's a table / relational / SQL API on top of the dataset API. Okay, so this is the world's quickest introduction to stream processing. You have unbounded dataset, we're going to call a stream. You have some code that you want to write that operates over the events coming in this stream, and then you have some sort of output from this as well. Both things are infinite data sets, so just unbounded streams of data. This model allows you to do really simple things like filtering or transforms, basic ETL type stuff. think like in terms of like map and filter, things like that don't require state. Much more interesting model is this. This is what is the big difference kind of in like the newer generation of stream processors is their state. And this is a much more general purpose model. So if you think about it, like if we all had computers that didn't have memory, like we could only build certain kinds of applications, right? This is the new model where this is really a general computation. This is general, you can do basically anything with this. So this is a big difference. And it's not that people never had state in stream processors before, it's just that the stream processor didn't know anything about the state. So it couldn't manage it for you. And when you can't manage it, you can't sort of guarantee like consistent computation. Where in this case, we can process messages, and then build up state over time, and then output data streams as well. And the input and the output can be decoupled, and you're building up this state over time. So with this model, you can basically build just about anything you want. But the important thing is that when there are faults, this state has to be managed fault tolerantly, right? So in Flink, you can guarantee that state is correct in the face of failures. And in stream processing, we tend to talk about, I think they're a little bit unfortunate terms, but they're already out there. So people talk about at least once semantics and exactly once semantics. In Flink, you can guarantee exactly once semantics with regard to this state here. It doesn't mean you're processing every message exactly once. It means that the state you're computing is as if each message was processed exactly once. And that is new. So another way to say it is just you get the same results if there are failures or if they're not. This is a very nice property, obviously. Okay, and then we don't really just like have one little operation we want to run over streams, but we tend to connect these things into graphs somewhere or another. In a nice API like Flink, as I'll show you, you don't really have to think in terms of this graph. You think in a higher level, more declarative API, but Flink builds this graph for you under the covers. But anyways, you might consume from RabbitMQ or some other queuing system, maybe files in HDFS. Read from Kafka is by far the most common. Kafka is kind of everywhere these days. Maybe you do some filtering or mapping. There's a join there, just like you'd think about in database systems. This is a stateful join or maybe a sum operation, and then you write to some sinks, influx maybe, or Cassandra, HDFS, back to Kafka. So we end up with these like networks of processes. Good? Okay. Okay, so we end up with these networks of operations. Data's flowing through this, through streaming fashion. In Flink, the data actually literally flows through this graph. And then we don't have just one instance of this, but we want to do this stuff over lots of machines, so we end up with something like this, distributed across a bunch of machines. We use those machines because either the data we want to process is coming at a very high rate, so think millions and millions of messages per second, or potentially the computation we're doing is extremely heavy. Either one of those two things, we want to use a bunch of machines to sort of do this computation. That's what Flink provides. And just as a quick idea, like baseline, benchmarking is a little bit nebulous always, but I've done a fair amount of it with Flink as well. And this is a benchmark I did with some hardware loaned to me by MapR. Some very hot hardware with 40 gig interconnect between all the machines. And on these 10 machines, I was able to achieve basically read a JSON message, grouped by key, and sum in a window. So a real sort of almost like a word counting type application, but also like a really typical analytics application. And on these 10 machines, I was actually able to get to 72 million messages. 10 machines. So Flink is very efficient. And it's very efficient. If you think about when you do this group by key and count thing, there's a full shuffle of data across the network. All the keys with the same value have to go to the same machine, so it's a shuffle. So full shuffle at this rate on 10 machines. That shuffle stage is something a stream processor has to be very good at, and Flink is very good at it. Okay. Robust stream processing with Flink. We're going to now get into writing some code, and this is going to be hopefully the more fun part. Let's get started. All right. So what I'm doing here is the size okay? Can you guys read it? This is like the most basic stub of a Flink program. And I guess I'd like to add here too, we haven't, if you wanted to start to play with Flink yourself, you don't have to even download anything. Just take a Maven dependency, work right here in your IDE, and do exactly what I'm doing, and that's how you can get started playing with it. You could be up and running on your laptop in a couple. You can start to play around. To start with, I'm going to define a stream, have a data generator for the purposes of this demo, and that gives us a stream. I'm going to gloss over the data generator because the other stuff that's coming is more interesting. I'm just going to show you what the data looks like, and we're going to move on from there. So I have this data generated from this data generator, and then I want to, let's just look at it. So the simplest thing in the world is like, let's just take a look at the data and see what it is. We're just going to run it here so we can get a sense of what we're actually even looking at. Run it in my IDE here. It's literally like when I run in my IDE here, a little Flink cluster gets spun up right here in the same JVM process, and it's exactly the same code that runs on it. But yeah, so the data is, it's a timestamp, it's some tag, and some value. So the tag is, the idea of the demo is we're sort of simulating IoT data. I have 3 sensors. I have a temperature sensor, I've got a pressure sensor, and I've got a door sensor, so just like open, close. And I've built this data generator so that the temperature sensor is just a square wave. It's easy to reason about. It's going to become important as I demonstrate some things. The pressure, I think one of these is a square wave, one of them's a sawtooth, and one of them. So we'll see when we look at it which is which. That's what the data looks like. But that's not as interesting as looking at it graphically, which is something I really like to do. So let's instead take the same stream, and we can write it to influx. Okay. So what I just did is added a sink. A sink is like something that's at the end of a data flow, and like data goes in there, and that's it. So in this case, I wrote this quick little influx DB sink to get a sense of like if you wanted to write a new one that Flink doesn't support out of the box, like this is it. This is the code. It's not that much code. Maybe this isn't quite production quality, it's more demo quality, but nonetheless, this is what it took to get data flowing. Invoke method. Sorry, I'm jumping around between Scala and Java a little bit. I've done this talk in both languages, so anyway, this is Java code. I was in Scala a minute ago. Nonetheless, you have this invoke method, and that's what you have to implement. Every message gets pushed into this invoke method, and you can do it. So this happens to be the influx one. And now if I go out here and I'm going to actually fire up influx, and I'm going to fire up Grafana, which is a really nice graphing tool. And we run this program. Should be able to, in theory, look at the data in Grafana. I think I want to make one change. Data generator. Okay. So we have temperature, pressure, and door. period of all of these waves is 1 second, just to make it easy to reason about. This is sort of the data we have. It's all one data stream, but in Grafana, it actually looks like, the raw data would look that. And if you kind of pull it out by key. So it's actually all one data stream going into Grafana. These graphs up above, filtered by, easy to look at. Okay, so that's our starting point. What next? The next thing I want to build, this. The reason I chose this is because it's a really common pattern, especially like in the kind of applications I actually see people building. This is a function. It's going to be, in our case, it's going to be an amplifier. And this is going to be a stateful function. There's a lot of stateful functions going on already, but I want to use this one because it's really clear what the state is. And if we're trying to like demonstrate fault tolerance and how all of this works, it's important that we can see that like this is actual stateful stuff. So this amplifier function is going to have 2 input streams. The raw data we just looked at, and then this control stream. And the control stream is actually going to be something we can type commands into, and I can change the amplification factor for each of those signals individually. Right? So I'm going to type at a command line, like in a socket, like temp, and then like 5. That's going to be the amplification factor for the temperature, etc. The state is obvious, well, maybe not obviously, but the state is going to be just that mapping between, for every key, some value, and that's the amplification. So we'll have temp is 5, pressure is 1, door is 3, whatever. So this could be any set of keys and anything you want for state, but this is what we're going to use for our example. So this is a stateful function, and we're going to output an amplified stream. And each of these inputs is going to be amplified different state. This is a really common pattern because what you have is, like when you have a data flow, the shape is basically defined, but you can get dynamic behavior this way. So a more real-world example might be like, imagine like a filtering system where the rules for like how to filter the stream and deliver them to different, say, customers or something is dynamic. And so you feed in the rules you have the main data stream, and you feed in the rules as a stream, and it updates the state here and affects the output of this filtering flow. That's actually a really common pattern. See a lot. It's a lot of like what we did at GNIP. You could build exactly like this. So let's build that next. What we need, first of all, is I'm going to add a new kind of source, and I'm just going to read from a socket. My machine. So then, let's see. We need to call this let's call this the control stream. And get a sense for the API. It's very much like the Scala Collections API or something. Not like really wiring up data flows. I think sort of compiles this into it. Well, but I'm going to now map this to, from this raw, we're going to have strings coming in on this socket. I'm going to turn them into a user-defined type here called a control message. And then I'm going to, let's see. I'm going to connect the 2 streams. This is going to be that sort of the 2 input thing that I just showed on the diagram. So I'm going to connect the input stream with the control stream. Then we're going to apply some function. In this case, it's going to be our amplifier function. And then let's look at this data. Okay. So basically, define a new input stream reading from a socket. This is basically just parsing the data into an actual control message. If we looked at the types here, maybe that's more useful. Whoops. What's going on? So we actually have a typed data stream, type control message, right? Because we've parsed it here. Rid of that because it's ugly. And then, this is what I love about Scala versus Java. It's just type inference. Looks much cleaner PI this way. Then we take the original stream and we connect it to that stream. So now we have these two inputs going into the same thing, and we have this flat map function. We look at this, again, sorry, this is now in Java. I'm jumping around, but we have two flat map functions, really. Flat map is just something that consumes some message and can output 0 or 1 messages. That's a flat map. This processes one side, the control message, and this processes the data stream side. Basically, though, all we're doing is when we get a control message, we're going to update some state. There's a key implied here because these are keyed streams. So for some key, it's the temp key now, I'm going to update the state to the current amplitude from this control message. So that just becomes the state we talked about. On this side, you're processing the data stream. All we're going to do is get the current state for that key and multiply by this amplitude. The data point by the amplitude, which is the state for that key. And now we have an amplifier. If the amplitude is, yes, so if you don't have the state for that key, there is a 0 state. So if you've never seen the key before, it's just 0. In fact, you can see that right here. There's a default value at the end there. That's the state. All right. So in theory, if I run this now, I feel like I've missed something, but once we have this all working, we can kind of we're going to need one more thing. We have to have somewhere to get data from. There we go. Okay. So I wish we had a little more resolution here. Input data is the same. This is that amplified stream now. It's just flat. Well, what we just built is this. So I can go out here, I can say for the temperature sensor, the amplification factor should be 1, pressure 2. This is just a socket. I just ran a little socket server in this window on the right. And then door is 3. Oops. I'll come back to there. Now we have these. See how each signal is being amplified according to this amplification factor. Make it really obvious. Say I just went and took one of them and said, that one. Does everyone see what's going on? Okay. So we just built this stateful amplifier. Now we can kind of play around with this. From here, we can play around a little bit. So the next thing I want to talk about is windowing. The reason is because just something really common, like I mentioned. You can't really do analytics over infinite streams. Just tend to draw windows, do aggregates, and do stats or something over. So how do you do windowing in Flink? This is something that should be really easy in a stream processor. So to do this, what we want to do is build some windowed analytics. All this. Yeah, like so. So for each key, you can think of key by in some sense of like, I've taken like this fire hose of all the data. I'm sort of grouping by key, and then whatever I do after this is like, you can think of it as just, that's like an individual stream. But I'm going to compute windows per key. So I can now say time window. There are various kinds of windows, but time window is the easiest to understand. Just a rolling, we call it a tumbling window. It's just, every second you're aggregating data every second, and then that's one window, and then the next second is another. They don't overlap or anything. There's other kinds of windows where they're sliding windows, so they actually overlap. One, like an hour aggregate, but you want to update it every minute. So things like, there's lots of different kinds of windows. This one is very easy to understand. Then we want to apply some function to the data in the window. In this case, I want to sum. And then we're going to, let's write this out and call it, whoops, also to influx. Call this sum. Okay, we have no, we're going to get back to this. We don't have our state here, so we came up in the 0 state. We don't want that to happen. That's going to be the next thing we talk about. But let's, for now, let's just make it a little bit interesting again. And then we have this. These summed, these charts here is that thing we just did. Windowing, and we have, if we looked at the measurement, it's called summed sensors. Actually, you can see it there. This is that windowing we just defined. Let's just focus in on this. I just zoomed in a little bit in time. Let's focus in on this pressure. Pressure sensor is a sine wave, okay? And its period is 1 second. And it happens to be time. This is all you. If you look at this summed pressure sensor, or if we sum a time sine wave over its period, what would you expect the answer to be? Just summing all the data points in a sine wave over its period. 0. Right, exactly. And should it be like sort of 0? Or should it be exactly 0? I would think we're trying to do robust analytics, we should get exactly 0. But we're not. We're sort of getting like around 0. Anyone have any ideas about why that might be? Not quite accurate. Yeah, I mean, that may be true, but if you're actually just windowing all those data points and summing them each second, I would expect to get exactly. Exactly. So what they say is like this is exactly one of the things that is important about event. What's happening when you're doing things in processing time is that you're just sort of like data's arriving at this machine, and every second you're sort of like grouping it based on like when it arrived at some machine. And think of there's lots of machines in the system, and then we're just like drawing these second windows and summing all the data that happens to fall in that window. And so you get sort of an approximate answer, but this is not a good way to do it. And think of this, like say we happen to like want to run this same code, but we want to like process the last month's worth of data. We don't want to process that in real time, right? We want to process it like as fast as we can and catch back up to real time. So we might use a ton of hardware and like process it 100 times as fast. You don't want this sum to be 100 times like what it is here, right? You actually just want to get the exact same answer you would have in real time. That's what event time is about. That and sorting out unordered data, both. But at the end of the day, we want to look at the time that's in the data, and we want to base all of the operations we do with time, we want to base it on the data time. Another way to say it, the way I reason about it, is we want to use, for anything we do with time in stream processing, we want to use a clock for the system that's completely derived from the data itself. If we can have sort of a clock that's derived from the data, then we're isolated from anything to do with data arriving in bursts or coming slow or coming fast or any of that stuff. So we want to extract a clock from the data. And that's exactly what event time is. So to make it, I have a slide about this, get a little bit more clear, I think. Green is event time, purple is processing time. The green is the timestamps in the data. And we're drawing these windows in processing time just sort of like based on when something arrives. So we're just sort of drawing our windows incorrectly. This is the error we're actually seeing. This is the error we're actually seeing. We don't want to do that. We want to do this, right? We want to get this exactly correct. And that's the idea of like robust time handling. One of the ideas. The other thing is we want to be able to do this even when all of this data comes completely out of order with respect, which is how it really happens in the real world. It never comes in time order. There could be lots of delays and things like are very sort of interleaved in terms of time. We still want to compute exactly the right result. And that's what event time is really. So it's actually important if we care about analytics. Well, if what we're trying to do, usually the time you actually want to use is the event, when the event was created, say, right? So like maybe even on the device, which might be some mobile device that actually, when did some event happen? That's probably the time you really want to use when you're doing analytics, right? Yeah, well, yeah, I guess that's sort of a separate problem. If you can't trust the timestamp that's in the data, sort of out of luck, I think, in some sense. Like, if you have a data set and all of the messages have some time that doesn't actually mean anything, I don't know how you can, like, exactly deal with that. But in general, what you can do is, like I said, I have some background from everyone's scrolling through their timeline whenever they happen to be doing that, and events are being generated all week on. And this happens at some given time. The data is timestamped on the device. Maybe they're off the network for a while, they're on a train, they go through a tunnel, whatever it is. The data comes in late, and it's totally out of order. That's the sort of thing we can do. But we're trusting that the timestamp in the data is, like, it means something. But you can sort it all out. And this is actually a pretty big deal. And so how do you do this in Flink is you just enable event time. Flink has a notion of different sorts of times. I think of them as different kinds of clocks you can use. And I just want to say event. The other two it supports are ingestion time and processing time. Processing time is what you already did. That's the default. Ingestion time is, again, this is a distributed system. So like when Flink first sees a message at the source, it can timestamp it. But then at least from there on out, it uses that time just like it would have been. That's ingestion time. It's not super useful. The other thing that is useful is Kafka. If you're using this with Kafka, Kafka has an ingestion time. So if you don't have good timestamp, you can at least use like C. Gives you some nice properties. Get the best properties when you actually can use timestamp. Sort of the further you get downstream, it kind of gets worse in terms of like repeatability and stuff. But these are the three that are supported. So we just want to say, hey, let's use event time. And then the one thing we have to do is the data, the real data we're generating has timestamps in it. It's just coming from the data generator. What doesn't is this stuff coming in from the socket that we added, this sort of control message doesn't have a timestamp field. So I actually have to tell Flink what time to use for that. And I'm going to do that the same way, yeah. So what you have to do is you have to tell it how to figure out what the time is. And I'll show you what this looks like. What we're doing is we don't really care about the time for these things. So what we're saying is just use the maximum time for these. And the reason the reason you use max is because as you have this local concept of what time it is on every different sort of parallel partition of all of this stuff. And Flink figures out at any given node what the current event time is by taking the minimum of all the upstream times. Sense? Because that's really what you're trying to calculate is when can time in event time progress at this operator. So it can progress to the minimum of all of the input. So I just say max here because that just sort of takes it out of the equation. Time can progress. Yeah. Yep. Yeah, so there's a couple different things there. So the idea, I'll go through it pretty quickly here, but maybe we can talk about it more at the end. The way all this works is based on something called watermarking. So what a watermark is that you have to have some way to say that, and it can often be very tied to the data set itself about it, but you have to have some way to say, after now, I don't expect to see data older. So this watermark is like a notion of commit. So you generate your watermarks. The simplest watermarking method is based on like, if I can just bound the times, I can actually come up with a reasonable. It's essentially just, it's pretty simplistic, but you're just sort of delaying. If the real time, or the most recent event time message I've seen is 12 o'clock, I'm going to say I don't expect to see. That's the current watermark is some offset from like the latest data. That works really well if you can just bound the skew. Yeah, so based on watermarking is how. The other thing you might use more of a heuristic or something, but you have to know something about it. Kind of the secret sauce. How do you exactly do general? Yeah, so no, you don't just put a delay into the whole system. What you do is this offset, say if you use the offset of an hour, the watermark being like, I've seen that this is the most recent method, so the watermark trails it by an hour, doesn't mean you can't get output from it. It just means that Flink won't consider time to have advanced past there. And what that really means is that if I'm computing some window, it will take an extra hour to get the final result that Flink considers complete. But you can then also do, we're not going to do it tonight, but you can do triggers, early triggers. You can actually, you have two different things here. You have watermarks, which is sort of like about completeness. I'm trying not to make this too confusing, but watermarks is about completeness. And you could have another concern, which is more of a processing time or a real-time concern with when do I want to generate data for download? Two totally separate concerns. So you can calculate this window, but you can give early results to download based on whatever, every second or some heuristic or whatever you want, so that downstream systems can still have early results. But then eventually you're going to say, okay, it's complete, and I'm not going to deal with this. And that kind of has to happen at some point, because you have to at some point release. So watermark is about complete. There's also early. real-time constraint. That answer. So that's what we were talking about. Yeah, so if you're wrong with your watermark, data comes, you said, hey, the watermark says I'm not going to see data anymore older than this. The real world, so you actually do, what does happen. That's actually up to you. You can either, there's a few different ways you can handle it. The default is actually to drop it if it's older than the watermark. But you can actually say, instead, well, I still have watermarks, but I want to keep around, basically it's just like a hint to Flink to keep around state for even longer, if you can afford the size. You can say allowed lateness is some value. And then if a late message arrives, actually just like merge in this message and re-emit a new. The other thing you can do, not in Flink 1.1, but in Flink 1.2, which is coming, you can actually, and this is the most realistic thing to do, in my opinion, you can actually have a totally separate path in your system. That's the most common like real world approach. You want to be really good with your watermarks. You want to get 99.9% right. It's very efficient. You compute all your aggregates in Flink. You write them to a database or whatever you're going to do downstream. Then you get some late data, but that should be a trickle. Unless your watermarking strategy is really bad, that should be a trickle. And with that, you actually want to merge in somehow down. That might require load some state from a database, merge in a result, and write it back out. So it's a different sort of path. But you have to be able to deal with late data. One of the primary tenets of both the data flow model and Flink, you actually want to solve real-world problems. This is the real world. So late data handling is fairly robust. You can do pretty much what you need to do. And sometimes people do just say, hey, if it's past the watermark, just depends on what your application. Okay. Where were we? So windowing, this, my opinion, processing time essentially. It has its uses for early updates and early results and things like that, but it shouldn't be correctness, event time. Okay, so what that brings us to next is failure handling. What we're going to do, we're going to stop running here in our IDE. I'm going to instead run a little Flink cluster. Laptop. It's a little easier to demonstrate failure scenarios this way. The other thing I'm going to do, I'm going to did I actually ever get to the point of showing that event time fixed the problem? I can't remember. Let's do that first. So I turned on event time. Let's demonstrate that it actually. So I have this state. All of them. Right. That's just my turn. That's dealing with, now the clock has nothing to do with it. Totally from it. This isolates this again. Tons of problems. That's kind of what the whole idea was, to demonstrate that. Shutting this down, running the Flink cluster. Instead, I just built the same code we've been working on in the IDE. This is how you launch a Flink job from the command line on a cluster. And I'll show you what the Flink UI looks like. Whoops. This is the Flink UI. This is the job we just launched. By the way, I said Flink turns your code into a data flow graph. That's the data flow graph that shows up in the Flink UI. A lot of this is actually the data generator, to about here. But you can see like this is the socket stream. This is our amplifier function we built, this co-flat map. Then we have a couple of sinks. This is the window function, and then this is actually about generating the sawtooth, sine wave, square wave, etc. But this is, Flink shows you exactly the data flow graph that is generated. So there's sort of this, it takes your code, it sort of in a sense compiles it or translates it into this, what's called a job graph. And this is what Flink actually works with. And this is the same whether you're doing batch programs or streaming programs. At some point, everything gets turned into a job graph, and that's what the data flow, and like the engine actually knows how to run. The other cool thing about this I'll just mention is it's really fairly easy to put more APIs on top of Flink because of this. It gives you a target for sort of compiling some different API to something Flink understands. So you can actually run storm jobs, you can run cascading, scalding, MapReduce, a few other things, SQL, et cetera, because as long as you can take that and at some stage turn it into a job graph, Flink can execute it. It's actually a nice part of the architecture, do this target. Then down here, we have various statistics about like what each operation's doing, how many data elements it's seeing. And if we jump back to Grafana, and let's give some interesting state one more time. Oops. Yeah. So we have this interesting state here. Now what I want to do is actually simulate a failure. And the way I'm going to do this is I'm just going to actually go and kill. It's just like knocking over a machine, basically. I'm going to go and kill one of the task managers. Just brutally kill these processes, I mean. And I'm zoom out in time. We can see. Oops. Far. So clearly we're not getting any data because one of the task managers is the process that actually runs. So in a real cluster, you've got lots of task managers, typically one per machine, and that's where like the actual worker code runs, like where your code runs. And we killed it. If we were running on Yarn or Mesos or something, Flink would have recovered like that already. The job would still be running. You'd almost not even see the fact that there was a failure. But in this case, the way I'm running it, it's you can see Flink trying to restart the job. But if you look here, it says there's no task manager. There are no slots available. Essentially, I'm playing the role of resource manager. I'm Yarn or I'm Mesos, and it's waiting for me to say, here's some resources. So let's see what happens when I give it back resources. The way I'm going to do this is just say, I'm just going to add a task manager back to the cluster. You can get it come up here. Job is now running again. Look at this. Zoom out again a little further to make it clear. Okay, so great. We're up and running. That's good. Normally that whole process would have happened really quickly because there would have been more resources in the cluster. But we do have this problem. There's like all this data missing. That's obviously not good. If we go and look at like this whole thing, we clearly lost all of our data. So that's not good. This is what we want to fix. We want our computation to be exactly as it is. So when we come back up, we should come back up. We should be processing exactly in the stream where we were, and we should have exactly the same state that we would have had if there were. All of our sums should be correct, all of this stuff. So all we have to do is essentially turn on fault tolerance. And frankly, there is literally no reason you would ever run. I'm only doing it for demonstration. I'd be happy to talk about it more later, exactly how all this works, but it's very efficient. It doesn't cost you almost anything in terms of latency or throughput. This is like one of the things that I think is exactly how this works. But there's a great paper written about it. It's called Lightweight Asynchronous Distributed Snapshots. sort of one of the things that. So you always run with this tree. This is what gives us exactly what's guaranteed. So when this is enabled, yeah. So every second, yeah. And what this basically means is every second, Flink generates these consistent cuts, if you want to call them that, like consistent snapshots. And these are place states that Flink can return to and continue computation when there's a failure. So if you lose a machine, you can actually bootstrap a new machine, go back to this consistent point on that machine, and continue the computation. So, is this text actually? I just said, show me the currently running jobs. I'm going to cancel the one that's running, which is the one old code. Pull this guy. I'm going to rebuild our code with this one change. I just turned checkpointing on. Then I'm going to run the job again. Pick up. Amplify. Everything's back to the 0 state again. Let me give us some interesting state to look at. So we have the, what did I just do? So the temperature sensor, the fact amplification is 1, door is 3, pressure is 2. And have these continue. So this time, I'm going to do the same thing. Going to kill a task manager. Show that we're down. We're not getting any data anymore. Okay. Here, there's just no data coming in anywhere in any of these graphs. And now I'm just going to add, so I could show this. Flink's trying to restart. There's no resources, so it can't. This time I'm going to add the task manager back in. And what I expect to happen this time is like, you shouldn't even see a blip on any. Pick up exactly where we were. All the states should have been the same as if nothing. Task, start. See what does happen. There. So that is stateful fault recovery. It could have been down for any period of time. We picked up exactly where we were, and we just do the computation. This should be exactly correct. We don't see a blip in any of our sums. We don't see no gaps. All of the state is exactly as it is. So that is stateful stream processing. That is a big difference from what. Yeah, the solution is, I mean, the solution today, unfortunately, is to over-provision a bit so you have resources available to catch up. The solution in Flink 1.2, which is 2 months from now, is to use a different parallelism and just use more resources to catch up and then scale back down. That's what you do. Okay. And truly dynamic scaling is coming in the sense that like Flink itself will just simply, that will probably not land until Flink 1.0. First quarter next year, fully dynamic scale. It will just scale out in order to catch up and scale back in. Okay, so the last thing I think we have to talk about, then we'll done. Oh, 2 things, but they're quick. Second one's quick. Downtime handling. So downtime handling is kind of what you were talking about in a sense. Like we actually have planned downtime, or we need to like say upgrade our cluster. For some reason, some of the software on the machines that are running Flink have to be upgraded. You have to upgrade Mesos. You have to upgrade Flink itself. You want to change your code, whatever. You need to have a way to be able to like shut down a computation directly yourself in a way you can manage and like then go back to that state and like restart. And let me show you what I mean. Then we'll talk about even more about like how. So this is our running job. What I'm going to do is take a save point for this job. Okay, a save point. So that's all we had to do. What a save point is it is a global, consistent snapshot of all of the state in your streaming job. Right? So it's like literally think of it as like a point-in-time snapshot of the whole state of this distributed. And then it's been saved, in this case, to this file path. In a real production environment, it would be saved to whatever state backend you're using, probably be H. Just some blobs of data we have to store. But essentially, this represents a consistent state in the company. And now that we have this, we can return to this state at any time. So we could make these every week, every day, every hour if we wanted to, every month, whatever. And we can always return to this point in time and continue processing it. Yeah, basically just return to some point in time and continue processing. So this is the way you would handle things like code upgrade, upgrading of the cluster itself, these kinds of things. Like you want to change your code because there's some bug and you want to like go back to 2 weeks ago and reprocess. Yep, question? Yeah, it depends. It depends. So if you reuse the same operators, you can load the state from those operators before. If there's wholly new operators in the system, there is no state to bootstrap, right? So it is something you do have to manage. Like we have to be careful with this. And it is something you have to sort of think about and evolve over time. What state? What states you have created and how you're going to like kind of go forward with the application. So there's a lot of power here, but we definitely have to be careful with what. Okay, so we have this point. We've made this save point. Our job is still running. We haven't done anything except for take this. These are the amplified sensors. This panel's just confusing, so let's get rid of it. This is the amplified sensors here. Maybe I can do something huge again. But remember, we've already made a save. So what I want to show here is now that we have this save point, I can actually do something crazy like just get rid of the Flink cluster. Okay? So there is no Flink cluster. Our application's down, but we have this save. Something we could do is we could actually say we wanted to actually migrate this application. Completely other cluster, maybe even in a different data set. As long as we had access to the save point, we can spin up another cluster completely somewhere else and resume this computation. Right, with all these in-flight state and everything else exactly as if nothing. Even on a totally different cluster. Right now, there is no Flink cluster. But what I want to try to demonstrate here is if I do start a new Flink cluster, I should be able to pick up my application like nothing happened. We should be in exactly the state we were in. And that state is this state. It's not this one. This is after I made this. So I want to see everything. And I want to see no data gaps. Let's see what happens. So I've run this cluster. I want to run a job from a save point. This save point. And job as before. And what I hope to see happen is that we're able to like continue this computation. See what does it. So that to me is it's a very cool thing. So there's some period of time where there was not even a Flink cluster. But nonetheless, we resumed our application, all that in-flight state, exactly as if nothing. Could be a totally different cluster. But our application is able to resume. If you think about this, you can actually do things like, you can make these consistent points, and you can like have one version of the application continue, and you can like change some code, and you can have like start that code from the same save point and goes like this. And now you can like do A/B testing. But you know they're in the exact same state where they started. So you can actually look at both, and you can actually think of like, well, maybe I could branch again. And a lot of crazy things you could think about doing. Like you think of almost like Git for like the state of an application, having different branches going. But the important thing is basic stuff you actually need to do stream processing. How do you manage upgrades? All kinds of stuff I just showed you. You have to be able to do this stuff, and without something like this, you're kind of on your own. It's not supposed to you. And the reason is because this is stateful computation. You can't just go back to zero state. Back to that. You have to be able to recreate state. And sometimes things have to come there. So you have to be able to do something like that. And then the one other thing I wanted to show, and then we're done. Let me just demonstrate. This is really quick. Let me just demonstrate reprocessing. So reprocessing is like, basically, I just want to change my code and reprocess all the data I've processed before. So let's just, what I'm going to do is change the period of all the waves we've been generating, just as a representative to code change. That's it. It's just a code change, and I want to reprocess the data. So I just changed my code. I'm going to build it. I'm going to kill the currently, and I'm going to run my job from that save point we already have. New code, same save point. There. So we literally just sort of, in a sense, we traveled back in time to some previous consistent point, and we ran from there with new code. You can see that because all of these sine waves have changed. If we zoom out further, even further, because I talk too much, you can see where more easy to see. That point right there is exactly what we reprocessed from there, from some known point. Yep. A gap in event time. Well, we traveled back to some known point, and we just continued the processing, so there shouldn't be any gap. You could see a discontinuity in the frequency of that wave, but we've regenerated new data. So that's time travel, if you will. Like, you can just go back in time and recompute. This is something that if you have a lot of experience with managing these kinds of systems, this is generally really hard. Doing this like with one. So that's kind of like similar to his question, right? Like, so if you've changed your program in such a way that like the code you want to run in the state you had before, you have to be able to manage it. What you can always do is you can load the state for stateful operators you have. But if you add new operators to the data flow, they're not going to have any. You do have to think about it's actually right now, if you like changed it in some incompatible way, Flink will. You can, I think it's already in master now. People actually sometimes you can recover like what you can recover and sort of go on if you really know what you're doing. That. The other thing you can do is you actually, the state that you're building that Flink doesn't manage direct. Well, there's internal state for windowing and all that stuff that Flink manages. It will always make sure that stuff's back. You can also build whatever state you want to build. And so you're sort of in charge of like exactly what that format should be on when it's saved and stuff. So you actually have control over like the serialization format for your state. So you do have to be. It's an area that I think will probably need some work. It is possible to do it correctly, it just takes care. So that was that was reprocessing. And I think that brings us end. Data Artisans is hiring, so if you're interested in this stuff, come talk to us.
Let's take about 10 minutes for questions. Get my attention so I can get you the microphone.
Yeah, so I had a question regarding these complex event graphs with all these operators you have.
Yeah.
How do you handle triggering and back pressure between different components? Some might be slower or faster just in the processing that they need.
Yeah.
How do you handle that?
The back pressure, because it's a streaming architecture, is actually super simple. You get back pressure in a very natural way. It's simply that because it's a real data flow, when some downstream operator cannot accept any more data, back pressure just sort of trickles upstream. Eventually, it's going to get to the source. You're expecting, typically, you're going to use something like Kafka. I mean, not necessarily, but you could use something like Kafka. Data ends up getting buffered in there. Eventually, you sort of up. But you don't have to like configure back pressure. You just get it very naturally. No, I mean, so if you have most interesting stream processing, if you think about it, there's probably at least one data shuffle, group by key. And so almost all of the, like, there's like some downstream node, like say the one we're computing a window, an aggregate on. It has to have input from all of the upstream nodes. So just by the semantics of it, you can't actually make progress if like one of these upstream partitions is completely unavailable. Well, you can't make progress anyway. But it's not synchronous. So if you actually had built a graph such that like these partitions don't actually ever have a key by, so they're just like embarrassingly parallel, they can progress independently. So the back pressure just happens automatically where it needs to for. There's a protocol between all of the, so like if you imagine all of the task managers have open sockets to them. There's a protocol that's very much like TCP windowing over that connection, and that's how it works. Similar to, there's another standard that's like, there's something out there called the, what do they call it? Reactive Streams Protocol. It's similar to that. It's not exactly compatible. Similar idea. Anybody else?
Jamie, is a great talk, and I enjoy it very much. So I got two questions. One is a very simple one. So is this code going to be in GitHub somewhere we can play with?
Yeah, it's actually already up because I used this talk at OS. So there's already a Git repository.
So maybe you can share with the members and so later on,
yep.
And including these additional, graph tools and all that stuff, right?
Yeah, and the other thing we have is actually on Data Artisans site, Mike Winters did a blog post that actually walks through.
Cool.
So you can just completely repeat.
Okay, cool. So, I'll probably find a link and share with everybody.
It's easy to find.
Okay, so the second question is, okay, so, one common question is Apache Flink can always compare with Spark's Spark streaming. So can you comment on that? So see what's the pros and cons?
Yeah, so I mean, I would say the biggest difference, and it depends on which version of Spark streaming you're about, but in all cases, the biggest difference is like this is an actual streaming. You get a lot of nice properties. That said, what's missing, honestly, as far as I understand, most of Spark streaming, everything we demonstrated here is actually missing so far. Like I don't mean to sound like an ass. I'm just saying, you don't have event time support, so you can't do out of order data processing and get correct results. You don't have anything like save. You do have the checkpointing mechanism for fault tolerant. It works a bit differently. I don't think it's. I'm not an expert there. I don't think it's nearly as efficient. A bit about how it works. And there's no actual streaming. The batch processor and what it does, and there's a big architectural difference. There's a direct trade-off between. The reason is because consuming data, you're batching things up. Say we have a 1 second micro. Then you want to like execute this on a cluster like a batch processor. In order to do that, to actually achieve any parallelism, you need to block it up further. Have little things you can actually execute in parallel on the cluster. So this is just how all batch processors, kind of like how map works or any of these sorts of batch processing, they all work the same way. So you take this micro batch and then you have something called a blocking interval, and you block it up further, and whatever those little blocks are sort of your unit of parallelism, then you fire those off onto the cluster, task starts up on the cluster and processes. That's how the whole thing sort of. Whereas Flink is just like spin up a graph of processes and data literally streams through. They're just completely different. And the problem with this, the reason you get such this throughput latency trick, batch process. At some point, scheduling these tiny little blocks comes all over. So these gets really big, different, or like sort of this dive. When latency gets low, throughput gets. That's one of the biggest differences. The rest are about semantics. There's a lot more stuff you could talk about in Flink. All the different kinds of triggering, all this sort of more flexible. Mostly derivative of or working in conjunction with like. A way to sort of like idea of it. So there's a lot of semantics, more rich semantics. We didn't cover it. Yep. Yeah, like they're using Spark, or they want to use Spark streaming maybe because they're already using it. Yeah, I mean, there are those are all valid things. Some people are actually, though, one other thing I want to like kind of put out there is the way I see together is that what Flink's really oriented towards is running these sorts of jobs robustly. Sort of continuous processing. Really what it's got. Plus these semantics are on how to do like more complex event time related things correctly. And some people are actually currently even they're building models for example. Like online scoring, they actually score. Because that's the system, 24/7. That's what Flink's really good.
I think we just have time for one more question.
Okay.
Just real quick, coming back to that question with the merge, you mentioned, so basically, I can give an example. Let's say you have a trading solution, right? And people buy, let's say, stock, and then on a daily basis, you create a position, and then a client, it's an accounting system, right? Someone goes back 7 days and then says that, hey, I forgot to file this ticket, this trade, and then you go and file it, and then you have to replay the entire thing for 7 days. You have to change the positions on a daily basis. So Flink would know the logic how to process and aggregate these tickets together into positions. And my question is there a way to do this merge automatically on the Flink side instead of having a custom built logic to handle that ticket?
I think not exactly, no. I would say no, not for free. What you're really talking about is like time series maintenance. Like you've got a whole time series stored in a database and like something changed and you want to go and like update time series and maybe even like derivative time series. I would say not for free. Exactly. It's something that's come up a couple times, but it's not, you could build that on top of Flink, but you're not going to get as You're not going to get all of that. You're going to have to come up with a way to manage the sort of time series. What you're usually doing in stream processing is processing like the current head of the stream, and you don't have as much freedom to move throughout history arbitrarily. That's kind of, for that kind of application, you can build it on top, but it's...
Okay, thank you to our speakers. Let me get them around. One quick announcement. Our next meetup is currently scheduled for December 5th, but we might have something announced for November, so check the website. And